Hello everyone, Phil here, today talking about science and getting it right, hopefully. So a few weeks ago, I found myself having a conversation about a certain thing called climate change. You might have heard a thing or two about it. Let me be clear, it is a real thing and it has been proven beyond any reasonable doubt. And while the other person was by no means denying this, I found myself almost failing as a scientist by the virtue of being unable to provide one clear, simple explanation without having to resort to generic statistical correlations. And as you might have heard, one of the biggest mantras of science is correlation does not mean causation. So when scientists see a strong correlation, doesn't matter how uncanny it is between two variables, they will go forward and look for a cause for this correlation. If you're a climate change denier, I don't think this video is going to change your mind. Maybe yes, what do I know? Whatever, it's not the main point of this production, really. I only intend to share how we can establish beyond any reasonable doubt how we came to the conclusion that humanity is the main culprit of the currently rapid changes experienced by Earth's climate. Now, I won't be able to go through all the possible evidences, because there are indeed a lot of them. I'm just going to focus on one single case study, just an example, which is isotope geochemistry. If you don't know what it is, you came to the right place. Because isotopes are cool, I like them a lot. This is not a scientific paper also. It's a video on the internet. It's free to make, not peer-reviewed, and I do whatever the hell I want with it, right? I guess that's the spirit, at least. Let's talk atoms. You're probably familiar with those consisting of three types of particles. Protons and neutrons, which are clumped together in the nucleus, and electrons, which orbit around it. For the scope of this video, let's ignore electrons and just focus on the nucleus. Now, protons are positively charged, and they define which element we are looking at. If we change the number of protons, we get a different element. And this number allows us to describe all the elements in the periodic table, which is somewhere around here. Neutrons, instead, are not charged. They still have a mass, very similar to the protons, actually. And for the sake of simplicity, really, let's just consider them to have equal mass. If we change the number of neutrons in the nucleus, we still have the same element, but we get what is called a different isotope. Now, before we get too deep into isotopes, I want to point out one thing. You might have seen various representations of atoms with the particles looking like tiny spheres. And I would argue that those really don't make much sense because they are based on an antiquated model developed by Ernest Rutherford in the early 20th century, and that's not really how atoms are believed to look like anymore. So I think that the best way to visualize the nucleus of an atom is just a list of particles, kind of like this, really. In red we have the protons, and in green we have the neutrons. They're usually called out this way. And I kind of realized while recording this that this can be a bit problematic for colorblind people, and I don't really know how to deal with that because these are the standard colors, really. So just keep in mind, protons are above, neutrons are below in this list, and you're gonna be fine, really. So let's look at hydrogen as an example. Its isotopes, which you can see here, more or less, are very easy to understand and to visualize. Now, the first two of them are protium and deuterium, and those are stable isotopes, meaning that they will stay this way indefinitely. Third one instead, it's called tritium, and it's radioactive or unstable, which means that at some unknown point in time, it will undergo a radioactive decay by losing some energy and converting one of its neutrons into a proton, thus becoming a different chemical element, helium-3 in this case. You can see the decay reaction right here. Now, I said that radioactive decay occurs at one unpredictable moment in time. And while it is true for one single atom, we can measure how long it takes on average for a massive amount of atoms to decay. And this is represented by this value here, called half-life. Now, half-life means, in practice, that if we have, let's say, 1 billion atoms of tritium at a certain point of time, after one half-life, we will only have 500 million tritium atoms and 500 million helium-3 atoms, which are the product of the decay reaction. Got it? Cool. Let's talk about the other type of isotopes now, the stable ones. But keep that stuff about radioactivity in mind, because I have the feeling that it will become important later. So, as I said before, deuterium is a stable isotope, meaning that it does not undergo radioactive decay, and it remains this way indefinitely. Now, when we're looking at very heavy isotopes, radioactive or not, such as uranium-238 and uranium-235, which you might have heard about from nuclear energy, actually, the difference between their masses is so relatively tiny that it does not result in any appreciable difference in their behavior during chemical reactions of any sort. However, for light elements such as hydrogen, which we talked about up until now, or nitrogen or carbon, for instance, this is not the case. For example, an atom of carbon-13, like this, will have an appreciable difference in mass from an atom of carbon-12, this one, which is also carbon's most common isotope. Therefore, in certain chemical reactions, we can witness a phenomenon called mass-dependent isotope fractionation. This means, in very simplified terms, that whenever a chemical reaction occurs, the abundance of one of the isotopes relative to the other one, commonly referred to as an isotope ratio, will change between the reagents and the products. The cool thing about this fact is that we don't even have to know the precise reaction that is going on. We can still use the isotope ratio to track any changes in its dynamics. And this is what makes it so well suited for tracking climate change and humans' impact on it. This is where we go back to the starting point. Let's talk about carbon now. Look at carbon-13 and carbon-12 that I've mentioned earlier. These are the global abundances of the two isotopes, and so if we analyze any material that contains carbon, we should be able to detect that ratio, right? Wrong. That ratio, again, is a global average of all possible reservoirs that we have ever measured that contain carbon. Well, both isotopes, of course. Each one of those have a slight different ratio. That doesn't matter. As long as we can take one very well-known and easily measurable carbon container, we can see how other containers of carbon compare to it. In other words, for example, let's take the Vienna PD belemnite, which is usually abbreviated as VPDB. Belemnite is a fossil, and it's just a reference material, really, which is even just theoretical. It doesn't even really exist, but whatever, don't worry about it. If we measure the ratio between the two isotopes in this material, we have a perfectly functional reservoir which we can refer to when we are comparing other carbon containers too. It will get clear once we go further with this. Okay, what do we make of this then? We know that the processes that transformed the buried organisms into hydrocarbons that we now burn as fossil fuels must have had some effect on the isotope ratio in those fossil fuels. I mean, those are massive and extensive geological processes. Something must have changed, right? If we compare the isotope ratio in the reference reservoir, so the VPDB, to the isotope ratio in the hydrocarbons, we get what is called a delta 13C. So delta carbon 13, delta being a Greek letter, and it's usually used for variations in scientific literatures, and indeed that's what we are doing now. Now, if humans' activity caused a major influx of CO2 in the atmosphere from burning fossil fuels, which we did, again, that is undeniable, we should be seeing this in the isotope ratio in the atmosphere. We should be seeing this changing, actually, right? The isotope ratio of hydrocarbons, especially of coal, but oil is not far behind, is a lot lower than in the VPDB. And therefore, lo and behold, that's exactly what we see. Starting from the Industrial Revolution, we see the isotope ratio in the CO2 in the atmosphere drop quite steadily, with a sudden dramatic increase in the rate of dropping, well, from the 1950s, which is when humans' industrial activity really kicks on after World War II. This is cool, isn't it? Still not sold on this theory? Well, let's look at another isotope of carbon then. Carbon-14. Now, this one is a radioactive isotope, and its half-life is about 5,000 years. So, you might have heard already about this isotope, because it is widely used in archaeology and similar sciences to date stuff, because its half-life is very compatible with the timescale of human history, and by the virtue of being a carbon isotope, it is found in pretty much anything that is organic, and humans are organic indeed. How do you date stuff with a radioactive decay? That's a great question. For another time, though. Someone should really make a video about that, huh? Let's go back at one thing I said. It is found, because it is carbon, in pretty much anything that is an organic molecule. And hydrocarbons are organic molecules. But is carbon-14 present in hydrocarbons? I'm glad you asked. So, carbon-14 forms high up in the atmosphere because of the bombardment of carbon dioxide by cosmic rays. That's cool, right? In some rare occasions, a very high energy photon, like an X-ray or a gamma ray, will collide with...
Hold on there. I kind of blundered it up here, so you're just gonna get this very cheap voiceover as a quick fix. So what happens is that a high energy neutron impacts in the atmosphere with a free carbon-13 atom, which is then thus transformed into carbon-14 with the addition of said neutron to the nucleus,
which will then be mixed up in a carbon dioxide molecule, which will then be taken up by a plant, which then might be eaten by an animal, which then might die, and it's a long, lengthy process, okay, that takes life forms and transforms them into hydrocarbons. And someone should really make a video about it, but that's not me right now explaining this. Let's just say that carbon-14 ends up either into a coal or an oil reservoir, right? Just take it as granted that at some point it happens. Or does it? See, even if some carbon-14 atoms manage to make it down to an oil or coal reservoir, it's actually going to be very, very few. Close to none, actually. But just because, remember, I told you, the half-life of carbon-14 is about 5,000 years. But these processes, these are geological processes that convert life forms into hydrocarbons. Thus, they take tens of millions of years at least. So by the time the reservoir has formed, the oil and coal reservoir, there will be close to no carbon-14 left. So those reservoirs will be carbon-14 free, pretty much. So wanna guess what happens when you burn fossil fuels extracted from carbon-14 free reservoirs? This happens. We add carbon-14 free carbon dioxide to the atmosphere. Therefore, the delta carbon-14 actually decreases in the atmosphere, despite the CO2 levels rising. This effect is called the Suez effect. I have no idea if I'm pronouncing this right, but wanted to give credit to the scientist who discovered it. And it's probably the best, in my opinion, evidence that we have of the immense impact that humans are having on CO2 levels in the atmosphere. There's also another way to produce carbon-14 and introduce it in the atmosphere, and it's blowing up massive amounts of nuclear weapons. I'm in no way justifying the slew of atmospheric testing that we performed in the 50s and 60s, but at least we got some interesting scientific data from those. Now, the more eagle-eyed viewers might have noticed that this graph that I showed you actually starts from 1969. Now, this is partly because I have the sense of humor of a 12-year-old, and partially because in the 60s and 70s, we had the biggest peaks in nuclear atmospheric testing, which looked like this. So, on the y-axis on the left, we have the total yield of bombs detonated that year, and you can see what carbon-14 does. It follows perfectly, with a slight delay, the amount of nuclear weapons detonated in the atmosphere. It's almost uncanny, really. So what does this tell us about the humans' impact on CO2 emissions? Nothing, really, actually. It's just very cool data that I wanted to share. Really, that doesn't add nothing to the discussion. So, here you go, you got free information about nuclear weapons. Why not? Let's wrap this up, shall we? Did we really need another geeky scientist talking about some obscure topic about climate change? I can think of two reasons for this, actually. So, first, I find these data very cool, and I wanted to share them with the world. And secondly, perhaps more importantly, I have seen so many people chiding others for not following the science. And while that is understandable to be salty, and because of the incredible amount of evidences we have for the human's influence on climate change, sometimes it's good to explain how those evidences have been found and what they actually are, instead of just being aggressive to other people. So here's a drop in the ocean, I guess. I'm not trying to convince anybody. I just hope that some people get more interested in this topic by seeing this video and maybe do some further research of their own. Again, I'm not an activist. I'm just a scientist. I'm not good at convincing other people. I'm afraid that's somebody else's job, really. So I hope you enjoyed all of this, and if you know of somebody that is a bit doubtful of the evidences behind humans' impact on the global warming that is going on, well, you can show them this video. It's probably a bad idea, actually. It's very poorly made. You know what? You can explain those topics yourself if you feel you have understood them well enough. Thank you very much for following, and until next time, see ya!
Thank you very much for watching. Just forgot to mention the main sources I've used. Here they are, gonna put them in the description as well. From those you can find all the data that I've used in this video. And that's really all for me this time. Bye bye!